Hey folks, in this video we're going to introduce the concept of conditional probability, which is completely opposite from independent probabilities, where in conditional probabilities, that is when the probability of an event is considered but under a particular set of circumstances. So this is not independent. However, the probability of this event of interest is conditional or dependent on something else that came before it. So this is going to be the first video in a few videos about this. Here I want to introduce the concept in a hopefully intuitive way with some examples that are pretty straightforward. In the next videos, we'll do some more rigorous calculations. Let's consider an example here with the standard deck of 52 playing cards. And let's suppose that you're about to play a strange little game. In this game, you, for some reason, can see the suit that you have, but not the value. So we mentioned in a previous video that we have the four suits. We've got the diamond, the heart, the spade, and the club. So you can see that it's one of those suits, but you cannot see, for some reason, that it's an ace, a 2 or 3, or a jack, queen, king. I would like to take an intuitive approach of addressing a conditional probability. No formulas, just intuition. Let's find the probability of selecting a king if you already know it's a diamond. So you already know it's a diamond. The event of interest is king. Well, we already know it's a diamond. A quarter of the deck is diamonds. If I was to circle those here, there they are. So we know that there are 13 diamond cards. And you know you've got one of them. That's what's known. The question is, what's the chance that it's the king? In these 13 cards, how many of them qualify as being a king? There's one king. That king is also a diamond, right? It's also a diamond. We have limited our perspective to only that of diamonds. So can we guess the probability of getting that king if we already know it's a diamond? Isn't that probability going to be 1 out of 13? I believe so. So we obtained this answer via intuition. Before I show you the formula, I want to sort of walk through in an analytical approach what we sort of just did. We essentially limited our perspective to that of only diamonds, that 13, right? So there's a denominator, and in that denominator was the probability of getting a diamond. In the numerator, we limited ourselves to those 13 diamonds, and we asked, well, how many of them are a king? Well, there was only one king. It's also a diamond because we're limited to that. So in the numerator, we essentially determined the probability of getting a king intersection and a diamond. This simplifies to 1 over 13, but if you started from scratch, the way this would likely have been written out was, well, there's 1 king of diamonds out of the 52 cards. And how many diamonds are there? Well, there's 13 diamonds out of the 52 cards. Those divisions by 52 would cancel, and you would certainly arrive at 1 over 13. Let's formalize this conditional probability into a formula so that it would work in any scenario. I'll scroll down here. We've got some notation that applies to conditional probabilities as well. The way this looks is the probability of an event. I'm going to call this E, and I just wrote a sort of tall vertical line. The way that is interpreted is given that. So that vertical line is given that. So this is saying probability of E given that F has occurred or is underway is, well, since F has occurred, we need to limit our perspective or our sample space to that of F. So we're only considering that this event has occurred. That was like the diamonds. Now that this has occurred, the main event of interest here is E. In the numerator, we want the probability of E, absolutely. But because F has already happened and we are limiting our sample space to F, E must be occurring with F. So E and F are considered in this numerator. A caution I must advise against here is this numerator. We saw the word and. We saw it in the independent events video. In this case, if 2 events are conditional, they are not independent. So here the word and is referring to the intersection, not to the multiplication rule for independent events. Events that are independent, you have to be very careful. That would have to be explicitly defined or known based on some sort of expertise. So this is likely not multiplication, most likely. I want to provide you with another interpretation of conditional probability. Let's consider the classic cup of marbles. There's 10 marbles in this cup, and 3 are red, 7 are blue. And let's suppose that you're going to select 2 marbles at random without replacement. So that means that when you select the first one, you throw it out the window, it's gone. And then you select the second one. Okay, let's find the probability that both marbles are red. Again, we're going to use our intuition here before I blast you with a formula. Well, probability that both are red. Both red. That must mean that, assuming that each marble has the same chance of being chosen, the first marble has a 3 out of 10 chance of being chosen, right? 3 out of 10. And then multiply. There are no longer 10 marbles in the cup. There are only 9. And how many of those 9 marbles are red? Only 2, right? So this is an illustration of conditional probability. This is approximately 0.06666666. I suppose if I put the bar on the 6, I can say this is equal. Now I want to discuss a formula for this. However, I want to do one more example with the cup O marbles. Gonna scroll down. This time, let's find the probability that the first marble is red and the second is blue. We're going to take the same approach. Probability. All right, first is red, and then the second is blue. We're starting with the 10 marbles in the cup. So it's going to be divided by 10. And since the first marble is going to be red, there are, starting with 3 red marbles, 3 out of 10. Again, sampling without replacement here, there will now only be 9 marbles in the cup. And now, well, how many of those 9 marbles are blue? The blue marbles hadn't been touched yet, so there should still be 7 marbles there, which is 0.2333333333333. Awesome. So hopefully you can see why this is some form of conditional or dependent probability. However, the way we're going to formulate our formula here is going to be a bit different. I want to identify what each of these fraction quantities would represent with probability notation. With the both red situation, the 3 out of 10 would represent the probability that the first marble is red, and this 2 out of 9, that's the conditional part. That's the probability that the second marble is red, given that the first marble was also red. Because that division by 9, that accounts for the without replacement bit, but that numerator of a 2 is accounting for, oh, there's no longer 3 reds because we took one out. So this was the probability that the second marble was red, given that the first was red as well. Let's do that same little process over here, where this 3 out of 10, again, is the probability that the first marble was red. But the 7 out of 9 is, that's the conditional part, the probability that the second marble was blue, given that the first was red. I think we are ready to formalize this into a formula. This is sometimes called the general multiplication rule, where the probability for E and then F to occur, sort of like first is red, second is blue, this and then that. So probability of E and then F there's going to be some multiplication here, is the probability of E times the probability of F given that E has occurred. You can sort of track back all the bits and pieces here where E was the first marble and F is the second marble is blue. Here, this applies to any two events. To any two events. However, there's a really cool connection if the events happen to be independent. If our two events of interest are independent, then notice that this quantity, the probability of E given F, that's this business right here. Well, let's intuitively think about that. What's the probability of the second event given the first event happened? Well, if the two events are independent, then it doesn't really matter that one event happened, right? It doesn't affect their respective probabilities. So this would just boil down to, well, get rid of F. Doesn't have any influence. Then substituting this bit here along up here with the light blue portion, then notice our formula turns into probability of E and F simplifies to the probability of E times, oh, this amount in light blue, we're just going to replace you with this light blue, probability of F. And so this light blue formula was shown in the previous video, right? This was the multiplication rule for independent events. And so it all circles back, it all is interconnected. This blue formula only applies to independent events. In general, this formula will apply to any two events. So, those are the formulas and hopefully some intuitive examples of conditional or dependent probabilities. In the next video, we'll do some more fun examples.